Bismillahirrahmanirrahim. Welcome to the course of Electric Machine 1, lecture number 2, week 2. In our previous class, we have studied about electrical circuits, some basics. Today we are going to study some more basic related to electrical and magnetic circuits. You already studied these things in your previous semester, but we need to revise and learn it in order to grip the course and learn it in depth. So let's start. Energy in an inductor. We all know what is an inductor. So a coil stores energy in its magnetic field when it carries current I. The energy is given by, we denote energy from W is equal to 1 by 2 Li square. W is the energy stored in the coil and its unit is joule. L is the inductance of the coil and I is the current flowing in the coil. Furthermore, when the current increases or varies, stored energy also rise and fall in steps with current. Mean when current increase or decrease, energy is also increase or decrease. Whenever current increase, the coil absorb energy, and when it fall, the coil release energy. Coil or inductor, we will study this in our machines learning, like the transformer winding, the winding in a stator or rotor. So energy will be stored or released there. So this is an important concept of the course. Another one is energy in a capacitor. A capacitor stores energy in its electric field when a voltage E appears across its terminal. The energy is given by W is equal to 1 by 2 C E square. E here denoted voltage, C capacitance of the capacitor in farad, and W energy stored in a capacitor in joule. Here, whenever voltage increase, the capacitor absorb or store energy, and when it fall or decrease, or we remove the source, the capacitor release energy to the circuit. Here is an example how energy is stored in circuits. In this example, we have a coil having inductance of 10 millihenry connected in series with 100 microfarad capacitor. Current at any instant in the circuit is 40 ampere and voltage across the capacitor is 800 volt. We need to calculate the energy stored in electric, mean in capacitor, and magnetic field, mean in the inductor coil at this moment. So we know that energy stored in the coil or in inductor is equal to 1 by 2 Li square. The value of L is 10 millihenry, mean 10 raised to the power minus 3. I is given 40 ampere, so 40 square. By calculating it, we got 8 joule. Similarly, energy stored in capacitor is equal to 1 by 2 CE square. putting the value, we have a capacitance of 100 microfarad capacitor. So this we put here, and 800 volts square. By calculating the energy stored in a capacitor, we got 32 joules of energy. Now, what is the relationship between magnetism and electricity? We will study this concept a lot in the course, so focus on it. Whenever an electric current flows through a conductor or a wire, a magnetic field is immediately brought into existence in the space surrounding the conductor. It can be said that when electrons are in motion, they produce magnetic field. Whenever there is a flow of electron or current in a conductor, a magnetic field will be produced around the conductors. One. The second thing, the inverse or converse of this is also true. That is, when a magnetic field moves relative to the conductors, it produces a flow of electron in the conductor. This phenomena, whereby in EMF and hence current there is flow of electron, is induced in the conductor, which is cut or is cut by a magnetic flux, is known as electromagnetic induction. Mean when we have a magnetic field moving or changing with respect to the conductor, it produces an EMF across the conductor, and with this current flow in the conductor. So in EMF and hence current flow of electron is induced in any conductor which is cut or is cut by a magnetic flux is known as electromagnetic induction. When there is current, there will be a magnetic field, and if there is a magnetic field changing, there will be current in the conductor. This is the comparison between magnetic circuit and electric circuit. We all know about the electric circuit, that we have a source, a wire and a load, and a source. This way we current flow, and we have a closed circuit. In a magnetic circuit we have a coil, MMF, with current flow in this winding. A flux is produced which is flow in this circuit. So in electric circuit a current flow, in magnetic circuit flux flow. What is flux? Flux is equal to magnetic motive force divided by reluctance. In electric circuit we have resistance, in magnetic circuit we have reluctance. Now EMF or volt is the source here in electric circuit. MMF equal to ampere turns is the source here in magnetic circuit. The unit of flux is Weber, and the current unit all you people know is ampere. In this way these all relationship and comparison you people can study it. You already familiar with it, just revise it and remember it. Now, production of induced EMF and current. A coil whose terminal are connected to a sensitive galvanometer G, it is placed close to a stationary bar magnet initially at a position AB. This is the circuit we are explaining this diagram. We have a coil connected with a galvanometer G, sensitive galvanometer. We have a bar magnet whose position initially is AB. AC, some flux from the end pole of the magnet is linked with or the coil, but as yet there is no deflection of the galvanometer. Initially there is some flux, but no movement detected by the galvanometer. Now suppose that the magnet is suddenly brought closer to the coil in a position CD. This is the new position of the power magnet, CD. It's come closer to the coil. Then it is found that there is a sudden but a momentary deflection in the galvanometer, and that this lasts so long as the magnet is in motion relative to the coil, not otherwise. When the bar magnet moves from position AB to CD, there is a momentary motion or deflection in galvanometer because the flux change in this coil. Next, the magnet is suddenly moved away from the coil. It is found that again there is a momentary deflection in the galvanometer, and it present so long as the magnet is in motion, not when it becomes stationary. It is important to note that this deflection is in opposite direction. Mean when we brought the bar magnet near to the coil in the position CD, a flux change, and we have see a momentary change or deflection in galvanometer. When we again move the bar away from the coil, there is again momentary deflection in the galvanometer in the opposite direction. As long as the bar is moving or the flux is changing, there will be detection. The galvanometer will move in one direction or in other direction. It will detect current due to change in EMF or due to change in flux. When it becomes stationary, there will be no change in flux and hence no current. The deflection of the galvanometer indicates the production of EMF in the coil. The only cause of the production can be the sudden approach or withdrawal of the magnet from the coil. It is found that the actual cause of this EMF is the change of flux linking with the coil. So I hope you people will understand how in EMF and current setup in a coil when a flux change. Faraday Law of Electromagnetic Induction. Whenever the magnetic flux linked with a circuit changes, as in our previous example, an EMF is always induced in it. Or whenever a conductor cut magnetic flux, in EMF is induced in that conductor. The magnitude of the induced EMF is equal to the rate of change of flux linkages. EMF induced is equal to minus n number of turns change in flux with respect to time in volt. So when the flux linked with the circuit changes, an EMF is induced in it. Or whenever a conductor cuts, mean the flux, the magnet is stationary and conductor is moving, an EMF is also induced in that conductor, and its magnitude is given by this equation. This is what called Faraday Law of Electromagnetic Induction. Now, what is the direction of induced EMF and current? Due to change in flux, EMF setup and current flow, what will be its direction? So a relationship exists between the direction of induced current, the direction of the flux, and the direction of motion of the conductor. The direction of the induced current may be found easily by applying Fleming's right-hand rules or Lenz law. Fleming rule is used where induced EMF is due to flux cutting, that is dynamically induced EMF, and Lenz law when it is used to change by flux linkages, that is statically induced EMF. So these are the two methods, that is Fleming right-hand rules and Lenz law, where we can find a relationship between the direction of the induced current, the flux and motion of conductors. We will study dynamically induced EMF and statically induced EMF in a coming slide. This is the right-hand rule. In this way we can, and this is the magnets, North Pole and South Pole. Here is a conductor. This is the magnetic field lines, and in the conductor we have motion in this direction. Field, first finger show the direction of field, second finger direction of EMF, and motion, the thumb show the motion of the conductor in a magnetic field. So this is called right hand rules. Now what is Lenz law? Lenz law is also used to find the direction of induced EMF and current when there is a statically induced EMF. This law stated that electromagnetically induced current always flow in such a direction that the action of the magnetic field set up by it tend to oppose the very cause which produce it. Mean when there is a conductor in a magnetic field and the flux changes or it cut the flux, there is a EMF induced in the conductor and a current flow in it. So this current always flow in such a direction that it set up a magnetic field which oppose the cause which produce it. What produce it? Change of flux. So it set up its own flux and it oppose the main flux. This is what is called Lenz law. Induced EMF. Now what is dynamically and statically induced EMF? We have studied this in that there is a right hand rule used when dynamically induced EMF and statically induced EMF. We use Lenz law to find the direction of current, induced current. So induced EMF can be either dynamically induced or statically induced. Now what is dynamically induced? Generally the field is stationary. Mean magnet is stationary, north-south pole is stationary, and conductor cut across it. Conductor is moving in this field, in this way it cut the magnetic field line as in DC generators. So this is called dynamically induced EMF. In second case, the conductor or the coil is stationary and the flux linkage with it is changed by simply increasing or decreasing the current producing this flux is in transformer. In dynamically induced EMF, the field or the magnet is stationary and the conductor is moving. In statically induced EMF, the conductor or the coil remains stationary and the flux linked with it is changed with the help of current producing this flux. So this is the difference between dynamically induced and statically induced EMF. No voltage induced in a conductor. We have studied that when the flux linked with the coil or conductor in EMF or voltage induced in the conductor. So how it happened? In many motors and generators, the coil move with respect to flux. The relative motion produces a change in flux linking the coil, and hence voltage is induced according to Faraday's law. In other words, when a conductor cuts the flux, a voltage induced across its terminal, its value is given by E. Induced EMF or voltage is equal to BLV. E is equal to induced voltage V, volt. B is the flux density, and its unit is Tesla. L, length of a conductor in meter, and V, relative speed of conductors in meter per second. In this, we simply discussing that in motor and generator, the coil move or with respect to flux, or the coil move in the magnetic field. In this way, the flux change in it because of its movement or rotation. The value of flux change, and in this way the EMF induced or the voltage induced in it have some value which is mathematically determined, or we can find it with the help of this equation. So this is example related to the voltage induced in a conductor. In this example, we have a stationary conductor of a large generator having active length of 2 meters and are cut by the field of 0.6 Tesla. And there is a conductor whose length is 2 meters. Active length means the length that is connected or linked with the magnetic field, and cut by the magnetic field of 0.6 Tesla, moving at a speed of 100 meters per second. Find the voltage induced in each conductor. So we have given data: length 2 meters, B 0.6 Tesla, and V 100 meters per second. We know that induced voltage is given by BLV. Putting value in this equation, so we got 120 volt. No force on a conductor in a magnetic field. When a current carrying conductor is placed in a magnetic field, it experiences a force which we call electromagnetic force. This is also the basic principal operation of motors. The force is maximum when the conductor is perpendicular to the field lines and zero when parallel to it. Mathematically, F, the force acting on a conductor, is equal to BIL. What is B? Flux density in Tesla, length L of a conductor in meter, and current in a conductor I. This means that when there is a current flowing in a conductor and we put this conductor in a magnetic field, it experiences a force. Why? Because when a current flowing in a conductor, a magnetic field produced around it And when we put this conductor in a magnetic field, it experiences a force because there is another magnetic field, that is the magnetic field we can call it, and there is another field that is produced by the motion of current in the conductor. So these two magnetic fields interact, and in this way a force acts on a conductor. This is the basic principle of operation of motors. In motor we use the same principle. Here is another example related to the force on a conductor in a magnetic field. A conductor 3 meter long carrying a current of 200 ampere is placed in a magnetic field and are cut by the field whose density is 0.5 Tesla. Find the force on the conductor if it is perpendicular to the line of force. Another thing to remember, that the force is maximum when the conductor is perpendicular to the magnetic field lines, and when they both are in parallel there will be no change in flux and hence no EMF induced and no force on a conductor. So in this example it is given that the force on a conductor we need to find if it is perpendicular to the line of force. So solution, the given data: L 3 meter long conductor, B the Tesla 0.5 Tesla, and I current in a conductor is 200 ampere. We know the formula, F is equal to BIL. Putting the value in above equation, so we got 300 Newton force exert on the conductor, which is 3 meter long and carrying a current of 200 ampere. Thank you.